Hello guys. So in this video or in this series of videos, I'm gonna go over a couple of examples related to rigid body dynamics and take a look at different situations that we might have to deal with and how can we use what we learned to address any specific question or problem uh, related to the motion, general planar motion of a rigid body. Okay, the first one is, we have a 2 kilogram bar. You can see the bar there. It rotates in horizontal plane. It's very important. Horizontal plane means there is no effect of weight in this plane. About the smooth pin, which means there is no friction there. And we have a 6 kilogram collar A slides on the smooth bar, slides on this bar, and the bar is smooth, means there is no friction between this collar and the bar. At the instant shown, at this specific moment, at the instant shown, R is the distance that collar has from this rotation, center of rotation is 1.2 meters, and the omega, the angular velocity of the bar, which is represented here in counterclockwise, is 0.4 radian per second. The collar is sliding outward because of this rotation, and the velocity of this collar relative to the bar is 0.5 meter per second. Now, if you neglect the moment of inertia of the collar, which means we can assume that this collar, this object is just a particle, meaning that forget about rigid bodies, look at just this one as a particle. Remember we said the big difference between a particle and a rigid body is that particles only have mass. We don't care how that mass is distributed. Whereas when you're talking about a rigid body, we do care about how that mass is distributed, and we care about the shape, the geometry of that rigid body, and that's how the whole story about mass moment of inertia came into play. So assume that this bar is just a particle, and we're asked to find the angular acceleration of this bar. We know omega at this moment, we want to find alpha. Now, let's see what can we do. Well, we're going to start looking at kinematics, right? So I'm going to write, let's put it this way, looking at the, looking at the kinematics Now, what do we have? I'm gonna put, well, I have to decide where to put my frame and to which object I have to attach it. Right? So I'm gonna put it on this point, right? This point that the bar is rotating around it, right there. And let's take this as X and this is Y. Right? That's the fixed point, so it's a good place to start, and I kind of know the relative velocity between this collar and the bar, so I'm going to attach it to the bar so I can take advantage of that knowledge, that relative velocity. So you can put it as attached to the bar. And you can also call this point O because we're going to use it. Just call this point O. Now, let's look at the acceleration. So I'm studying that color, so I'm going to put AA is equal to AO plus A relative plus alpha cross R plus 2 omega cross V relative plus omega cross R vectors. Now, well, the frame is attached to the bar, which means that, and it's at point O, so there is no acceleration for point O. It's fixed, it's just rotating. So this would be 0. There is no AO. And let's take a look at the rest of these parameters. I'm going to start with A relative. Well, A relative is the acceleration, the relative acceleration between the collar and the bar, right? Because the frame is attached to the bar. I don't actually know that, but because it's relative, I said the way you look at the relative motion is that assume whatever your frame is attached to is frozen. It's fixed for this specific calculation. Right? Assume that bar is fixed as a result because frame is attached to bar. Now this collar can only move this way. What is this? This is pretty much a linear motion. So the linear motion is a second derivative of displacement. It's nothing but r double dot. Do we know what it is? No, but we know there is an acceleration in this direction. And since along x, I'll just put it I. It's a positive direction going up. If you want, you can also draw the direction if it helps. That gives you, let's see, this is acceleration at that point, so let's just put it this way. Keep in mind x and y are tilted, so this is along x-axis. Second term, I'm going to write it here, is alpha cross r, angular acceleration, times r, the distance of the point that you're studying from the origin of the local frame. Now, well, the value of it, the magnitude of it would be r alpha. R is where the point is. We already used r to represent that distance, and alpha is the acceleration of the bar. Yeah. The direction of it, well, r alpha is always perpendicular to r, and since alpha, well, I'm going to assume that alpha is counterclockwise. I don't know that. We'll see at the end when we find alpha if our assumption is correct. We're going to get a positive value for alpha. If it's not correct, we have to switch the direction. There it is. And this would be r alpha perpendicular to this. And since that direction is along y-axis, that would be j. Right? Now, third term, I'll go for, let me put it here. I'm putting everything along. Well, let's see what is left there. We have 2 omega v relative. 2 omega cross v relative. Omega is vector, v relative is vector. Well, in terms of value, we actually know that 2 omega we're given is 0.4, and v relative, the velocity of a with respect to bar, is 0.5. So that's the magnitude. Direction, well, let's see what direction do we have. We said omega cross 2 omega cross v relative is perpendicular to v relative. If you go back and take a look at the notes and the way we defined this term, remember it was associated with Coriolis acceleration, and we said the direction, the way we deal with the direction is, I'll put it as a, 2 omega cross v relative is perpendicular to v relative. What is v relative? Well, v relative is along this line. Right. We said v relative, we talked about v relative. A relative is pretty much the same as v relative, the same direction. Well, can be opposite direction, but along the same line. So if that is v relative, or is perpendicular, I'm going to take it this way. Let me choose the right tool. There you go. Assuming that omega, well, we're already given omega, so that's the exact direction. Right? This is omega. Right? This is omega. So the 2 omega v relative is in this direction, obviously perpendicular to A. Last term is omega cross r. That term, we'll get omega cross, better way, omega cross r. This gives, well, the magnitude, well, it would be r omega squared. The direction, let's see. So if this is OA, let's say this is point O and this is point A. When we're talking about the direction of omega cross R, we said the direction is always from the point we're studying to the origin of the local coordinate frame. So in this case, it's the direction, the whole direction is a vector from A to O. So you can just put it right there. So that would be the direction. This is omega cross R direction. And this direction is negative I. This is X, so in negative direction along X. So what happens is that, so I'm going to put it here, A, right, the acceleration of A, the absolute acceleration of A is equal to, we're putting I and J components together, is R double dot minus R omega squared I plus, well, I have R alpha there, so R alpha minus, let me write it a better way, is R alpha minus, well, plus this calculation right here, which gives 0.4, plus 0.4. I forgot to put J here. This is in J direction. So this would be J. So this gives me the general form of the acceleration of point A, which I'm looking at as a particle. Now, a couple of things I know, right? I know what R is. I could just replace it here. I know what omega is, but I don't know what alpha is. And as a result, I can't, and also I don't know what R double dot is. So I have two unknowns, and I only have one equation. Let's see what else I can do. I have two things moving, right? I have a rigid body, it's a bar, and I have a particle, which is that color. So let's take a look at them, see what can we get out of those. Now looking at, let's say the color. So looking at the color, looking the color, let me try to draw something as close as I can to this color. Let's say this is the color there. This is rigid body, and I guess that's pretty much it, because I want to take a look at just this one. So this is a particle, so it has some acceleration. And let's use the same axis coordinate. This would be X, this would be Y. This color is in contact with the bar, so there is a reaction force on it, and that's it. Because we're in horizontal plane, there is no effect from gravity. Right? Let's see what we get. And on this color, well, obviously this is point A, so we have M. I'm going to represent the mass of the color with MC. MCA X and MCA Y. Okay, so summation of forces, well, this is just a particle, so there is no talk about mass moment of inertia, so that equation is out of the picture, right? We're just looking at a particle. So I'll just write down the second equation of motion, Newton's second law, not for rotation, but just for translation. That'll give me in y direction, well, this is n. In y direction, I have n, and then n is equal to whatever I have on the other side, which is mcay. Well, what is ay? Ay, I got it from before. This is ay, right? The y component of a, r double dot minus r omega squared, and I can replace r alpha plus 0.4. I can replace r, which is 1.2, and then just put it there. So go there. This would be mc times 1.2 alpha plus 0.4. Summation of forces in x direction is equal to max. What I get out of this? Well, let's see, there is no force on x direction, so 0 is equal to mc times whatever is the x component of the acceleration, which was r double dot minus r omega squared. If you plug in the numbers, you'll get 0.4 for that. Immediately from this equation, you can actually find r double dot. R double dot becomes, well, is equal to 0, so this becomes 0.4 meter per second squared. What is r double dot? R double dot was our a relative, if you remember. Was the relative acceleration. So we got that one. Now, we added the new equation, right, to the bucket. We had, what did we have? We have this one, which alpha and r double dot were unknowns. We added two equations, right? From one of them, I could find r double dot, which means two equations are left. But the problem is alpha was unknown. Now I added another unknown, and it's n. So I need to take a look at what is going on, right, with the bar. Right? So right now I have two equations. I got this, right? I used the first equation, plugged it here. I found r double dot, but now I have one equation and two unknowns again. I don't know n, I don't know alpha. So let's take a look at what's going on with the bar. That's the only thing left that I might be able to use to get another equation to solve for both alpha and n, right? If I want to find n. So looking at the bar, let me try to draw the free body diagram for the bar. This one was r double dot, a relative. The bar, let's say this is the bar for free body diagram, and then for kinetic diagram, I'm going to draw it like this. I have center of gravity in the center, it's a slender bar. We have the connection, right? The point here. Well, this gives me, I can decompose the reaction force into two vectors. Let's say I put this as OY and I put this as OX. Keep in mind this one was X vector, axis, and this one was Y axis. And there is no mass, right? It's in horizontal plane. Don't forget that. Right. I have rotation. Now we're dealing with the rigid body. What I'm going to do is that I'm just going to use the rotation, you'll see, around this point, and I write all the equations around this point, which makes my life easier because I can get rid of OX and OY. And I have the equivalent of force N now on the bar. There you go. This is N. It's the same N applied to equal and opposite, right? Newton's third law. For every action, there is a reaction, equal and opposite. So now I'm going to do is that I'm going to find the moments around point O, because if I write it this way, I can get rid of these two. Remember, we said we can write the moments about center of gravity and find out what are the components of acceleration of the center of mass and how do they create moments about the point we are finding the moments about. Or we can just write everything from the beginning about the point that we're interested in, right? In this in this case, point O. So that would be IO alpha, right? I could write IG, mass moment of inertia about center of gravity, times alpha plus M times whatever the components of center of gravity, components of acceleration are applied to center of gravity times d, the distance of those components. But I'll just write it this way. We can write both ways. This is just going to be a little easier and straightforward versus the other way. Now I have to find, well, it's a slender bar, right? So from before, we know slender bar's mass moment of inertia 1/12 ml squared about the center of gravity. I have to find the mass moment of inertia about point O, so I use parallel axis theorem, right? We said IO, or any axis that we're interested in, as long as that axis is parallel to the axis passing through the center of gravity, and we know the mass moment of inertia about the center of gravity, we can actually find the mass moment of inertia about that axis, as long as we know the mass and the distance between those two axes. So MB I used to represent the mass of bar. So for bar, about center of gravity, 1 over 12 MBL squared, it'll being the length of the beam, the bar, plus MB times L over 2 squared, the distance between center of gravity and the axis I'm looking at. You do the math here, you will get 1 over 3 MB L squared. And that would be IO. Now I have IO. I'm going to find the moments about point O. The only force creating the moment is N. And from there I can actually find alpha, because I'm going to get a second equation aside from this equation I had from before, and then I'll have two equations and two unknowns. So looking at the equation, this was I'm going to go back to summation of all the moments is equal to IO alpha. From there, well, all the moments I have N, so that would be minus N. Point the distance N has, well, that's R, and R was 1.2. I was given that value is equal to 1 over 3 MB L squared alpha. Right, I can replace N from before. Well, I have N here from the previous equation. So now I have two equations, this one, and two unknowns, N and alpha. So I replace N from the previous one to this equation. Right, I'll get minus 1.2 alpha plus 0.4 times MC, right? And then we have 1.2 is equal to 1 over 3 MB L squared alpha. Right? From there, we can actually solve this. You know MC. MC was actually, we were given, that was 6 kilogram, and MB was 2 kilograms. So we know both of this. And we can get alpha out of this equation now. From there, you can find the angular acceleration of the bar. You do the calculation. You will get minus 0.2547 rad per second squared, which tells us the direction we assumed for alpha was not correct, and it's in the opposite direction, and that's what the problem was asking us to find, the angular acceleration of the bar.